Hello, welcome to our next set of notes. We're on section 7C. Today we're going to talk about the law of large numbers, or the law of averages, as you might have heard of it called. And we're going to calculate some expected values. So at the beginning of this unit, when we first started off, we talked about relative frequency and theoretical probability and how they're a little bit different. Relative frequency, you actually do the experiment and you look at the results from that experiment versus, theoretical, where we think what should happen. In real life, what should happen doesn't always happen, right? Things don't always line up perfectly with what should expect to happen. You take a coin, you flip it, and you flip it 50 times, and you're expecting about half those times to be heads, because the coin is 50-50, the two sides. But sometimes you might get 20 heads, sometimes you might get 30 heads, or anywhere in between. We don't always get exactly what we theoretically should. Those don't line up perfectly. There's a little bit of variation there. The law of large numbers tells us that if you have a larger and larger number of trials, that these two get to be very close. That's the big thing about the law of large numbers. It says that as for sufficiently many large enough, the relative frequency probability and the theoretical are going to be close. So here's kind of the more formal statement. So the law of large numbers, if a process with independent results, so every trial is not affecting the other ones, things like flipping a coin, rolling a die, drawing a card, but putting it back in after each draw. For those kind of events where they're independent, if they're repeated over many trials, the proportion of trials in which it occurs, which would be your relative frequency probability, will be close to the probability, the theoretical probability. The larger the number of trials, the closer the proportion should be to the theoretical probability. So the more times you do it, the closer you're going to get to that theoretical amount. So the chart below, this is actually showing this kind of an illustration of this law of large numbers. So they had a six-sided die. They're looking at the probability of getting a 1, which is 1 out of 6, or 0.16 as a decimal. That's the theoretical what you should get. So 1 out of every 6 rolls should be a 1. You don't realize that doesn't happen every time, but that's about what we expect to happen. Then they ran a simulation where they sat there and they rolled the dice over and over again. And you see at the beginning, they're very far below this 0.167. The blue line is the theoretical probability level. But as they kept rolling, you see that they got closer and closer. There's a little dip here, but in general, they got closer to this level. Now, they did cross it, but they didn't stick right on it. You don't get to it and just stay there, because what happens is over time, you might go up or down a little bit. You can go above it, you can go below it. But we'll see that in general, the more trials you make, the closer you are to that line. You see how it's over time, the difference between the blue line and the red line is decreasing. The more trials you make, the smaller that difference is. And that's always going to be true. It might take a lot of trials. You see here, by the end of this, they're doing 5,000 trials. And there were times when it was, far away for a bit, but in the long run, it will always eventually, get closer as you go further out. And that's what the law of large numbers tells us. That for a sufficiently large number, as we get more and more trials, we're going to get closer and closer to that theoretical probability. And so we can kind of have an expectation, a little bit of expectation, that the number of results we're going to get when we actually do the trials, do the experiment, should be close to the theoretical, especially for larger numbers of trials. Now, this can be misleading, though. Some people take this as too much of a strict rule. Although it does let us estimate kind of the probable outcome about what we should get, kind of have some expectations. It does not guarantee a specific result will happen. So you end up asking people things like, well, if you flip a coin 10,000 times, would you expect to get exactly 5,000 heads? And people say, oh yeah, that's half the time. It's 50-50, so you should get 5,000 heads. Well, you should get close to 5,000 heads, but you could get 5,001, or you get 4,999. Those are both close, and they'd be very reasonable. There's no rule that says you're going to get exactly 5,000. So no, we wouldn't expect to get exactly 5,000, but we would expect a result close to 5,000. And we wouldn't be shocked if we got 5,000. because we're expecting something close to 5,000. Of course, 5,000 is close to 5,000, but we would not expect to get that exactly. That's the idea. So we're looking for, we expect something very close to 5,000, close to 50%. Because you're flipping a coin, it's 50-50. But we're not expecting that specific value to come up. Now, that's a misunderstanding of the law of large numbers. Just because you say, okay, well, we've done it 10,000 times, it's significantly big enough, you're going to get 5,000 heads. No, but you expect very close to 5,000. Just like here, we're getting very close to 1/6 of the time. We're getting this 1 on the 6-sided die. The number is getting really close to 1/6, but you'll notice it's still varying a little bit. It's still a little bit above. It's not perfect. Sometimes it's above, it could be below, but it's close. And again, it's getting closer as time goes, but there's no specific exact amount that's getting to. We don't know for sure it's going to be exactly this number. I think that's a little too extreme. It's probability, so there's a chance you can be a little bit over, a chance you can be a little bit under. There is still just that randomness, that chance. Okay, using this law of large numbers actually lets us calculate what we call the expected value. Expected value is a very useful tool for people that deal with probabilities. It's the estimated gain or loss from partaking in an event. So it's typically games of chance. You play lottery, you play poker, you buy a raffle ticket. Your expected value is a way to look at the average earnings or losses from that game of chance. So it's not looking at your total losses or earnings. We're not going to take this and say, oh, I bought 100 tickets. It's typically we say, okay, what do I expect to happen per ticket? So that's why it's an average, kind of on an average per ticket. That's my expectation. That's what expected value is. So looking at our estimate gain or loss, it could be either, because games of chance, sometimes you win, sometimes you lose. And the games can be set up good, against you or for you a little bit. We'll talk about it more. But it's the expected gain or loss from partaking in an event. Or think of it as your average earnings or losses from a game of chance. That's kind of the way to think about it. Now, the way we calculate expected value, we multiply the value of a possible result and the probability of that possible result. So we always going to multiply the value times the probability. What this does is it kind of accounts for the fact that, yeah, we could make $1,000, but there's usually like less chances of that than there's maybe chances of just winning $10. And so that $1,000, even though it could happen, it's a lot less likely. So it's not going to add as much value because there's a lot less chances of that happening. So the probability kind of adjusts those numbers. It takes the values that are there, and the less likely they are, the less they're going to count towards our expected value. The more likely they are, they're more going to count. So it adjusts all these values for the different outcomes, different possible results, based on their probability. We're going to multiply those. So we'll look at each result, and we'll find its value and its probability. We'll multiply those together, and then we're going to add those if they're positive gains, if we have a result like I won, or subtract those if they're losses. I have a result where I lost money because I didn't win the property. Now, a lot of times the game of chance, you'll have more than just one or two possible results. Yes, you could win or lose. So usually there's two. Sometimes there's more. Sometimes you have the grand prize winner, but you also have like the runner-up winners. People that get like second, third, or fourth prize could still get like money prizes. If you buy like a lottery ticket, Powerball ticket, stuff like that, there's the jackpot that everybody talks about all the time. But there's still like smaller prizes as well. There are $1 million prizes, there are $100 prizes, there are like $2 prizes. So the jackpot's not the only prize. So a lot of times you actually have to find this for lots of different results. You'll have to multiply the value and the probability for each result and do that multiple times. It just depends on how many results there are. So you kind of have to look at the situation and say how many different outcomes there can be. So we'll extend this as much as needed. That's why I put the ... at the end. On the formula sheet, it kind of just says, multiply the sum of the product of the value and the probability. It takes us to multiply, so add those all up. And so a lot of times I get students that get confused. They think there's only just two things to multiply. No, it depends on how many times, how many different results they have. So we'll do a couple. First one here, we'll have just two results, but later we'll do ones with more. And you kind of see how that works in practice. But that formula is on the formula sheet in a form, but again, I think people get confused about the formula. They're not doing the homework and practice with you. So make sure you really understand these in the homework and the quizzes. Okay, let's find the expected value of a dice game where you win $5, so it's a positive result, for every 6 you roll. So if you roll a 6, you win $5. But you lose $2 for rolling any other number on a 6-sided dice. So you got two results, right? Result 1 is a win, and result 2 is a loss. So this is kind of the most simple you can get, is you either win or you lose. There's only two options. That's kind of the simplest we get. First off, result 1, win. If you win, you got $5. That's money you brought in, you won. So we earn $5 for that value. Result 2, if you got that one, you lose $2. So we're going to actually be subtracting. We think this is kind of like a negative $2 because that was a loss. This one was a win, that one was a loss. So we've got to think about bringing money in versus money going out. First off, the winning one, the probability, well, you get a 6. Well, there's only 1 6 on the 6 sides of a die. So this is a 1/6 chance. So my probability is going to be 1 over 6. So there's a $5 payout, but there's only a 1/6 chance of that happening. The chances of losing, well, you lose on any other number. So all 5 of the numbers, 1 through 5, those are losers. So you get 5 out of 6 losers. For any other number, that's 5 out of 6. So your chances of losing are much higher, right? So this -2, the 5 6 is going to make it count for a lot more than like the $5 is only going to count for a little bit because 1/6 is smaller. So that's how expected value kind of works. It takes the value and you multiply it times the probability. So the value gets multiplied by the probability. The bigger the probability, the more that value counts. The smaller the probability, the less that counts. And then you put them all together. Here I'd have this is positive minus this amount. And that's how I do it. I do 5 times 1/6 minus 2 times 5/6. That will give me my expected value. I'm going to multiply that out. I'll go grab my calculator. So do 5 times 1/6 is my fraction minus 2 times 5/6. 5 times 1/6 minus 2 times 5/6, and we get negative 5/6. So this one ends up being negative 5/6. If you want a decimal, if you don't want a fraction, that times expected value, we calculate decimal because we're looking at money amounts, so that's pretty common. This option, your calculator does have a fraction to decimal button, so you just hit the second, and hit this F to D right here, and that's going to take that answer and turn it into a decimal. For a decimal amount, this would be about negative 0.83, because you have to round the 3 off to the nearest penny. This is a dollar amount, expected value. We are looking at dollar amounts. So we're expecting, on average, to lose 83 cents per game, per roll. So this is something that could really happen. This would be a realistic game. Someone could go play a casino or play with a friend or whatever. You could say, here, we'll play a game. I'll pay you $5 for every 6 you roll. You have to pay me 2 for every other one. This is how casinos make their money. This is how any game of chance gambling, they make their money, is they have it set up like this, where on average, most of the time you're going to lose. You're not going to lose every roll, but because some of those rolls you're going to roll 6 and you're going to win $5. If you're lucky, you're going to win enough, roll more 6s than the typical person. It might make some money. But we're not really expecting that, because on average, we expect by the law of large numbers, on average, that you should lose about 83 cents per roll. Now, let's note, you can't lose exactly 83 cents, right? Because the way this game's set up, you can either win 5 or lose 2. So if you play one time, your two options are either you lose $2 or win $5. You play 2 times, you could win a couple times, you could make 10. You could win once, lose once, so you'd make like 3. Or you could lose twice and make minus 4. So you can't lose like exactly twice 83, $1.60-ish. But if you played it a bunch of times, we would expect on average that you're losing about 83 cents per game. You could say, well, if I played it 100 times, and you could multiply this times 100, and you expect on average over 100 games, you would expect to lose about $83 on 100 games. Yeah, you might get some winners, but most of your things are going to be losers, because 5 out of 6 are losers, so you'd expect to lose more than you win. So expected value, it's a way to measure the probability of the game. Every casino does this calculation, expected value, for every game they have. And they know what the expected payout is. For them, it's positive. For the gambler, it's negative, and that's how it's set up. It's set up that way on purpose. It's actually legally, standardized. There's regulations and all that, but that's how it's set up. The casino knows that the more times people play their games, the more money they make, because the average expected value is for the casino, not for the person playing. So this is expected value. If you can find a positive expected value, that's great. It means you're going to win more than you lose. There's no guarantee, right? So someone could play a game with a negative expected value, and because of random chance, they might just win a couple times in a row, and they might come out a winner. That can happen. But they shouldn't go into expecting to win. That's where you're being silly, where you're not understanding probability. If you go into a casino and you expect to win, then you've fallen for some fallacies. You've misunderstood how casinos work. They make money for a reason, because everything's set up so that they are typically going to take in more than they pay out. That's their average. Okay, expected value gives us a numerical method for judging decisions involving probability beyond just casino games and gambling, playing dice games. Any type of situation where you have some kind of probability, you can kind of look at the chances of things happening. You can use this. A positive result, remember, would mean a gain. A negative is showing of a loss. Here, an insurance agent is going to use expected value to look at his policy, decide if it's good policy, if he sells it, if he'll make money. So he sells a policy for $1,000. Based on past data, there's a 1 in 100 chance a policyholder will make a $10,000 claim. So as the insurance agent, every claim someone makes, you have to pay that out. So if someone makes a claim for $10,000, you lose $10,000. There's a 1 in 500 chance that the policyholder will make a $50,000 claim, then you have to pay out $50,000. And there's a 1 in 1,000 chance the policyholder will make a $110,000 claim. And so you'd have to pay $110,000. We're going to use expected value to determine the profit or loss for this policy. So we have to think about the different results. So for, there's the first result, which would be the $10,000 claim. There's the second result, which would be our $50,000 claim. There's the third result, which would be the $110,000 claim. And there's one more aspect to this. So we have to think about the fact that there are some people that aren't going to, make a claim at all. And we have to think about the cost of this policy, how every person that buys this ticket, they're going to pay him some money. So at this point, you could try to figure out how many people aren't going to claim it, the policy, but that's kind of hard to do because we have all these different probabilities. They didn't really tell us how many people aren't going to make a claim. So instead, there's actually an easier way to do this. The way we deal with this, trying to pay for the policy in the first place, to include that aspect, what we're going to do is we're going to say, well, everybody has to pay that, right? No matter who you are, whoever it is, they're going to pay him $1,000. For every person he has, is going to pay that. So there's a 100% chance that they're going to pay $1,000 for the policy. So it's almost not a result. The other ones are what happens after, does someone make a claim? This one is kind of the setup. This is the, everybody has to do it. So I'm going to put everybody. A lot of times when you're doing chance like this, when you invest money, when you, sell a policy, stuff like that, there's something that everybody, has to pay. We'll see later, I'll do one with a Powerball ticket. You have to pay to get the Powerball ticket to start with, then you get your chances of winning or losing. So this is going to be included. The claims are going to be losses, right? So these could be I'm losing money because as a policy holder, he had to pay out in the claims. In this case, the pay-in is when he actually makes money. These are people buying it. So he could lose $10,000 if someone makes the first $1,000. They make the second claim, and he could lose $110,000. He makes the third claim, but no matter what, every person that buys, they're going to pay $1,000 in. That's what they're going to buy. This one, the probability is 1, which means it's guaranteed because every person is going to do this. They all have to pay $1,000. You can't get a policy without paying $1,000. No matter whether they make a claim or not, they have to pay $1,000. For the first result, make a $10,000 claim, that only happens 1 in 100. So there's a 1 in 100 chance you're going to make that $10,000 claim. Some policyholder would do that. For 50,000, we have that 1 in a 500 for the 50,000. So there's 1 in 500 chance someone's going to make that 50,000 claim. And for 110,000, there's a 1 in 1,000 chance, a 1 in 1,000 chance for that 110,000. So again, every time we look at the value times the probability, and we add those up, again, if it's a negative, if it's a payout, then it's a negative. We're losing money. We're thinking of this as the insurance agent. So the agent loses money every time he has to pay for a claim. So from his perspective, these guys are negative. From the policyholder's perspective, these actually would be positive because they would be making that money, but then this part would be negative. So it all depends on your perspective. There's always kind of the two sides of this: the person giving the money, the person receiving the money. So like the last one, we had the winner loser, the person doing the dice game, us, where we won 5 for the roll 6. We had a negative amount, but the other person who took our $2 had a positive 83 cents per cent. That's what we're talking about with the casinos again. On their side, they're the ones getting paid. It looks great. This is kind of now we're working the other side. We're looking at the agent. He's hoping for a positive amount when we're done because he wants to make money with this policy. Okay, so let's look at his value. So we're going to take all these and we're going to add and multiply stuff together. So we're going to do a negative 10,000. Hopefully, yep, 10,000 times 1/100th. You could just do a division button instead of using the fraction. It doesn't really care how you would do it either way. I'm just going to use fraction button because it's the calculator's fraction button. Okay, minus 50,000. 50,000, and then this one is times 1/500 minus 110,000 times 1/1,000. So far we've just looked at the payouts, but he also is bringing money in. So we have to say, okay, every person's going to pay him $1,000. And this one is times probability 1. It's guaranteed. You really don't have to multiply by times 1 because 1,000 times 1 is still 1,000. But because that one's guaranteed, he's going to bring in $1,000 for each person. And we look and say, okay, is this a good policy for him to sell? And he actually $690 per person. Now, of course, you can't make $690 on one person because they're paying $1,000 or they're making a claim. Those are the two options. So either the person's going to pay him $1,000 and they're not going to get any money back because they never make a claim, or they're going to pay him $1,000 and then they're going to make a $50,000 claim. He's going to pay out $50,000. But on average, across all his customers, on average, he's going to make $690 per customer because he's going to balance off his payoffs, the claims, with all those people buying the policy. So this one would give us $690, and it is positive. So for this insurance agent, this policy is great. Everyone he can sell, he's going to make $690. Now, not exactly, but on average, we kind of know that that's typical. So the more he sells, the more money he'll make. So for him, he wants to sell as many policies as possible. So for example, how much would he make if he sold 1,000 policies? Now, he knows that he's making $690 per policy. So this is, expected value. That's about how much he makes per policy. And, he's looking at $690 per policy. So what he could do is he could take his $1,000 times 690. And he could say, I'm expecting if I sell 1,000 policies and I'm expecting to make about $690 per policy, multiply those out, I get 690 with 3 more zeros. He's expecting a payout of about $690,000. Now, he could get exactly that. He might make more, he might make less. There's probability, there's chance involved. But he's going to expect to make, somewhere close to that number. Again, we saw that earlier with the flipping coins, saying you don't get exactly 5,000 out of 10,000, but you expect close. And so by using this expected value, he's going to expect close to this. And that's how insurance actually works. This is what they do. An insurance company, that's why one of the biggest jobs you can do as a mathematician, if you go get your PhD in mathematics and stuff, you can study and become an actuary. And they work for insurance companies. And they calculate the probability of certain things happening, the probability that someone will make an insurance claim. And the insurance companies take that, they take these numbers, these probabilities, they calculate the expected value, and they design their policies so that they will make a decent amount of money for each policy sold. Those are how their policies are built. That's why something that's more likely to have flooding or hail damage is going to have a higher insurance charge, because they say, hey, well, we want to make sure we make money when we sell insurance. So if you are more likely to have hail damage or have flooding or have some other kind of thing, we're going to charge you more for your insurance than someone that doesn't have as much chance of those things happening. And that's how it works. That's how insurance works. So a lot of people don't make a claim. The insurance company just takes their money and keeps it, and then they pay it out to the few people that do get to make a claim, get to or have to, whatever you want to say. And that's how insurance works. You're kind of hedging your bets. As a policy buyer, you're saying, well, I don't want to be that person that needs $110,000 to pay for something and didn't have insurance to cover that. Then I had to just pay it out of pocket or borrow money for it or something. If that thing happens, then the insurance company would have covered it. But the insurance company knows that most people won't have that. So most people, they'll just pay the money in, and the insurance company will just get to keep it. And that's how the insurance works. All right, let's do one more. Let's do the Powerball. Now, I did simplify the Powerball because the actual Powerball has even more options. The numbers not as nicely rounded to zeros. So I made it simpler. But let's look at the expected value with the Powerball with lottery tickets. Now, you go buy a Powerball lottery ticket, and you're hoping to win some money. But the Powerball, the lottery company, expects most people not to make money because most people buy losing tickets. So we're going to figure out, okay, what's our expected value? Now, we do need to know what the Powerball is, the jackpot. So today, the day that I'm doing this, right now, it's actually kind of a small jackpot. The jackpot is only 30 million. It's fun. Jackpot small. So the jackpot is 30 million right now. That's the prize. But we got to be careful, because when you win the jackpot, yes, you have a $30 million prize, but that doesn't count for the fact that when you win, you don't get to keep $30 million. You actually end up having to give away a good chunk of that in taxes. So and if you take the lump sum, where if you win the Powerball and you get all the money at once, you actually also get less money because of that. They only pay out the highest amount if you do like the annuity, where they get paid over years. But let's pretend for simple, say you take the whole amount, and then typically if you take the whole amount at once, you're going to be in the highest tax bracket, and you're going to be taxed at 37%. So out of your 30 million, you're not going to keep all of it. You're going to keep the other 63%. So we're going to multiply times 0.63. So your actual prize, even though the lottery advertises 30 million, after taxes, you actually only bring in 18,900,000. I know that still only is silly, because that's still a huge amount of money, but it does make a big difference in calculating our expected value. Since that is the biggest prize, if you try and include it with tax, it can make the expected value look really good. But if you actually take out the tax, like you're going to have to. In fact, even the $1 million, $50,000 prizes, you technically probably should take away the tax amount. I'm not going to, just to make it simple. But if you don't take away those amounts, it can kind of be misleading. So let's see what happens for expected value on this. And again, I've rounded these a little bit, but yeah. So the Powerball jackpot, that 18 million. There's only a 1 in 292 million chance. $1 million prize, 1 in 12 million. 50,000 chance of prize, there's 1 in 900,000. $7 prize, 1 in 300. That's fairly common. A lot of people win like $5, $6, $7. There's a couple more options in there, but I simplified to make this not a super long problem. So for each result, so each one of these is going to be a result. So we have 4 results. We're going to have to do the probability plus the buying the ticket. That'll be our 5th result. It's not really a result, it's just something everyone has to do. Okay, so the first one, you make 18,900,000, but you only have a 1 in 292 million chance. So it's going to be 1 over that 292 million. Plus the next one, you have $1 million prize. but that only has a 1 in 12 million chance. 1, 2, 3. You have the $50,000 prize, but that only has a 1 in 900,000 chance. You have the $7 prize, and again, these are all positive because these would be winners. These would be where you're making money, but that only has a 1 in 300 chance. And then you have to account for the cost, right? So right now, if I did this, it would just be positive because I'm only bringing money in. I don't have any negative amounts. But I have to pay for the ticket, and everybody buys a ticket. The tickets cost $2. So we have to subtract $2, and since everybody pays that, probably that happening is 1. So that's going to be a 1. So this is a pretty common technique, this whole, you look at all the positive stuff, and then you take away the cost at the end. And it's an easy way to figure out that we have to include the cost, because if you don't include the cost, it's going to make everything look always like a, positive expected value because you forgot to charge for the ticket. So accounting for the cost is important. And again, since everybody pays it, it's got probability of 1. So that's going to be part of our answer no matter what. That's why we're going to do it. You could just take all these other parts and just subtract $2 for your ticket, and that would be fine because that's what's going to happen. 2 times 1 is 2. So that's the kind of the big part of doing expected value is you have to remember to account for the cost of the ticket, that kind of stuff. So ticket price. All pay. Everybody pays that $2. And it's important because, there's chances of winning these big prizes, but there's a guarantee of everybody having to pay that $2. All right, now the fun part, we can type all this in our calculator. So I'm going to just type this stuff in. So 18,900,000. I got to make sure I don't type anything incorrectly. That's 1 fraction. And I've got 292. 1, 2, 3, 1, 2, 3. So 192 million. Plus I have that 10 or the $1 million prize. 1, 2, 3 times fraction. I got 1 over 12 million. Probably put it maybe a little bit more where you can see it. Okay. And then I've got that 50,000 prize times 1 over 900,000. And there's the $7 prize times 1 over 300. There's only 1 in 300 tickets wins that prize even. And then don't forget the minus $2 for buying these tickets. And so your expected value in this case is negative 1.9 rounded up to 1. Negative 1.91. So this would give us negative 1.91. So even though there's a $18,900,000 Powerball, even in that situation, we're still expecting that on average we're going to lose $1.90 per ticket because there's so many losing tickets. Out of every 300 tickets, only one of them makes $7. The other 299 tickets are losing $2. Out of every 50,000 tickets, or 900,000 tickets, only one of those makes 50,000. The other 899,999 are losers. They already lost $2. Think about that. That's they're bringing in 900,000 times 2. That's $1.8 million, and they're only paying out 50,000. If you think about it that way, right? That people buy $1.8 million worth of tickets. One of those people might get the $50,000 prize out of those 1.8 million paid in. That's how this works. So it's negative 1.9. Even if you go back and do this again and say, let's say the Powerball is even much better. So let's say it's this time it's 90 million. So instead of 18 million, it's 90 million. So 90, 1, 2, 3, 1, 2, 3. So 90 million for the jackpot. Even if you own a really big prize, 90 million. Still a negative 1.66. I mean, we could even go more extreme. What if there's actually $1 billion prize or something like that? So instead of just $1 million, I'm going to put in an extra 1 here. So now I've got one, 1, 2, 3, 1, 2, 3. So there's hundreds, thousands, millions. I've got $1 billion prize. Say that happens. then you'd finally get a positive. So 1 billion, I guess 1 billion, that's a billion prize. That would only happen if the prize was actually 2 billion and closer to 2 billion. So this is not even like, this isn't, oh yeah, I got to $1 billion, now it's positive. And again, this is only going to actually really matter for that one person that won the jackpot. The other 292 million people, because this is rounded a little bit, are not going to make any money. They're not going to get a prize. So it's only going to be that person, that won that Powerball. The rest, that doesn't even really matter that much because it's, chances of getting that one ticket are not good. But typically, you'll get even a negative on the Powerball. So expected value, this is telling me that, yeah, I'm not going to lose $1.91 on a ticket because the tickets cost $2. But I expect on average over a bunch of tickets that I'll lose about $1.91 per ticket. So what we can look at is think about how some people will sit and play the lottery over and over again. They'll play it weekly, they'll buy multiple tickets to increase their chances. I put that in quotes because it's not really increasing your chances. It's just spending more money. Yes, you have more tickets, you have a slightly better chance of winning, but you're never going to have enough millions of tickets to actually have a decent chance of winning the Powerball jackpot. So what if someone buys 10 tickets a week for a whole year? How much are they going to make? Well, if I look at that, so, okay, 10 tickets a week means I'm buying 10 tickets times weekly. That means there's 52 weeks in a year. I'm buying 520 tickets. For those tickets, I'm expecting, on average, each ticket to lose about $1.91. So I would multiply that by negative 1.91, and that would tell me my typical profit. So I do 520 times negative 1.91, and I would expect to lose almost $1,000 on those tickets. And this is how the Powerball makes their money. This is why the Powerball is a thing. This is why we say, oh yeah, it can fund our schools, because people that buy it, very, very few of them win. There's always someone that that will win eventually, but typically the majority of people don't win. They just pay in money. They pay in thousands a year, and then they go, well, I had a chance of winning, and they paid $1,000 just to have the hope or the chance of winning. And it's just a misunderstanding of probability. If you really think that you're going to win the lottery, you just don't really understand probability. Chances of you winning are just almost nil. Very unlikely. You're just throwing your money away. I've known math teachers that bought lottery tickets. It just broke my heart because if you understand math at all, you understand that buying a lottery ticket, you might as well just take your money, burn it, and just be done with it. Because your chances of winning the lottery are so slim, that 1 in 292 million chance, it's so slim, it's just not even worth it. You're just throwing your money away. Might as well just take it and throw it in the trash. There's so many other things you could do where you have at least a little bit of a chance of making some money with your money. There's other options. Buying lottery tickets is a terrible way to spend money. You're basically guaranteeing that you're going to pay money to the government. It's a tax on people that just don't understand that. That's what it is. So if you're buying lottery tickets, you're just throwing money away. It's not a good use of your money. I'm not saying you can't go gamble and can't go buy lottery tickets. That's up to you. But you shouldn't do it with the expectation you're actually going to win. If you're doing it with the expectation you're going to win, you just don't understand math. You're just not doing it correctly. You're not thinking about it correctly. You're thinking that you're going to be the 1 in a million. And they're not. There's millions and millions of other people. One of them's going to be the 1 in a million. Okay, that's expected value. That's the main math in this section. We do have a couple more things to talk about. Some of the fallacies, some of the trip-ups, the reasons why people do such a bad job with probability. I think that's one reason why this section is so important, because so many people just don't understand probability very well, and they let it, trip them up. They fall for a lot of these tricks that casinos and other people do. The first one people misunderstand is what's called the gambler's fallacy. So the gambler's fallacy, when you have someone that's sitting there in their at a slot machine, they're pulling the lever over and over again or hitting the button over again, and they say that they've had lots of losses in a row, so now they are due. Means they think that they're going to have a win because that's going to come and make up for their losses they've had already. That's not true. This is called the gambler's fallacy. And a lot of people think that because of the law of large numbers or the law of averages, that things have to balance out. That, oh, well, I lost earlier, so now I got to win. But that's a misunderstanding, because every time you play that game, the probability is not changing. It's always got the same probability. And these games of chance, these casino games, stuff like that, they're set up so you have more of a chance of losing than you do winning. And that's not changing no matter how many times you play the game. So the gambler's fallacy, again, this is mistaken belief that a streak of bad luck makes a person due for a streak of good luck. That's not how this works. The trials are independent. Probability of winning does not increase. So the probability of winning does not increase because they are independent. Every time you pull out the leverage machine and you pull that lever, you always have whatever it is, maybe like a 0.1%, 10% chance, or maybe it's even less of winning. I just make it a number. You have a 10% chance of winning, but you also have a 90% chance of losing. And every time you pull that lever, that's true. Doesn't matter if you lost 30 times before, this next time you pull the lever, you still have a 10% chance of losing. Of winning, sorry, and 90% chance of losing. Doesn't matter what's happened in the past. It's not going to change. Yes, eventually, this thing is going to get closer to the law of large numbers. Now, what's, I think, really misleads people is they think, well, if it has to get closer to the law of large numbers, that means they have to make more money. Eventually, doesn't it? And it doesn't. I'm going to show you an example why. So often the gamma fallacy comes from, incorrectly understanding the law of large numbers. You think that just because you're getting closer to that theoretical probability, right now I'm losing more than I should. I'm below the 10%. So eventually I get closer to 10%, I'll do better. That's not how that quite works. So here's an example. This kind of illustrates, it's not really a homework question, but it just really illustrates how the gamma fallacy can be misled, how people get into that because of that law of large numbers. Say you play a simple coin flipping game. You win $1 if the coin lands on heads. You lose $1 if the coin lands on tails. You're expecting to win half the time, right? 50-50 heads and tails. After flipping the coin 100 times, you have gotten 45 heads. Okay, so far you did 100 flips. Heads, you got 45. That means that tails is 55, right? Because if you flipped it 100 times, 45 plus 55 will give you 100. And your profit, well, how much did you make on this game? Well, you made $45 for the heads, but you lost $55 for the tails. So you have this one's positive, this one's negative. 45 minus 55, you actually lost $10. So you're down 10, but you're saying, hey, you know what? Not a big deal, I'm down 10. But I know the law of averages, law of large numbers says that I should be getting heads closer to 50% of the time. I'm only at 45%. The percent right now, this is 45%. We're a little bit below where we should be. So you say, you know what, I'm going to keep flipping. So say you go back and you keep flipping, trying to get this game to the point where you get close to that 50%, and you can make some money back. How about you get 1,000 flips in? You really kept at it because you were like, I lost some money, but I got to keep going. And you know that eventually you're going to get closer to 50%. Let's say you do. Let's say you get 48%. So that 48%, that is closer to 50%. You're doing better now, right? But 48% of 1,000 is actually 480 heads, which means that out of 1,000, you've had 520 tails. So even though you got more percent, you're actually losing more money now. Because if you look at this $480 of profit, of income, of revenue, minus the $520 losses, you're actually down $40 now. So even though it has gotten closer to 50%, you're still losing more money. And it could get even closer. Say you played it like 10,000 times because you're like, you know what, the more times I play it, the closer I get to 50%, I make more money. And you've gotten to like 49.9% wins. You're getting really close to 50%. At this point, 49.9, well, you move this, do that times 700,000. So 100, I put 100,000. Yeah, we'll say 100,000. Okay, you have 100,000 times 0.499. You have brought in $49,900 because that's how many flips you've had. But if you have 49,900 heads, then tails, you've actually had 50,100 tails. You should add up to 100,000, which I just wrote down here. I did 100,000 flips, I guess. And when you subtract those, this one is bigger, so you actually still have more loss. $200 difference? So you actually are lost $200. So even though, yes, you kept getting closer and closer to 50%, your losses just keep increasing. And this is a really fair game, right? This is 50-50. It is possible you could play long enough. Eventually, you'd get back up to 50%. It might even go above 50%. And that could happen. That's chance, right? There's random chance. But it's also possible you could just keep playing and playing and playing and losing more and more and more money. And what happens is most people can't keep playing to 49,000, right? They can't keep just going and going and going. Eventually they'll hit a number where they say, I can't afford to lose anymore. And that's kind of what the casinos, they back on, they bet on, they depend on. They know that most people can lose up to a certain amount and then they have to quit. And so the casino can just sit here and do this all day long. They can let you play as long as you want until you quit, because they know on average they're going to be making money from you most of the time. And so they can lose a little bit here, lose a little bit there. They can even lose a big jackpot here or there. But on the average, everybody's going to play for a while and quit, and the casino's going to take whatever percentage of their money. Even if they didn't, even if some people win, the casino's going to make money in the long run. So gambler's fallacy, again, it's all about just because you lost for a while doesn't mean you're going to win later, because this can happen where large numbers can be satisfied. You're getting closer and closer to 50% because heads should be showing up 50% of the time. Doesn't mean you're going to almost win. And again, it's also depending on the fact that they're independent. The chances from previous ones do not affect the chances in the future. That's a big part of this too. So just because they lost 5 times in a row doesn't mean the next one I have better than 50-50 odds. This is like those families that say they have like 3 kids and they're all girls, and they go, I wanted to get a boy, so they have a 4th kid. And they say, oh, because we had 3 girls, we're more likely to get a boy. That's not true. Every time you have a kid, it's 50-50 chance. What the gender of the previous kids are does not affect what the probability of getting the next one is. That's not how that works. It's just a 50-50 chance every time. Okay, last page. So streaks, another common misunderstanding. This is another thing people do. It kind of contributes to the gambler's fallacy of people misunderstanding things, is streaks. So I got 2 possible results of flipping 6 coins. So you flip a coin 6 times. You flip this coin 6 times. One result was heads, 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 heads. Right, 6 heads. The other one was heads, tails, tails, heads, heads, tails. And which one is more likely? And typically people look at this and say, well, this one's really weird and rare, so it's less likely. It's going to be this one's more likely. And they're wrong. Because these are equally likely. Those are equally likely. They both have the same chances of occurring. What happens is people look at this one, they say, hey, that's the event of all heads. There's only one way to get that. That's a big deal. And they say this one, oh, that's 3 heads and 3 tails. And there's a good chance of getting 3 heads and 3 tails. But the problem is this is not 3 heads and 3 tails. This is heads, tails, tails, heads, heads, tails. This is one outcome. And your chances of getting this one outcome are the same as the chances of getting this one outcome. But humans, we're designed, we're the way we work. We notice streaks, we notice patterns. It's part of how our makeup is, how we understand the world. We look for patterns and we identify patterns, and we see a pattern like this and we think, oh, that's a pattern. It's special. It's different. It's unique. That's less likely. And we look at that and we don't see any patterns. We think, oh, it's not that big a deal. There's no pattern. There's no streak or anything. And so then we make false assumptions. Here we say, oh yeah, you have a 50-50 chance of the next one being heads or tails. And we say here, oh, well, it's very unlikely you're going to get heads again, so it's probably going to be tails. It's more likely to be tails, which is false. The next flip still has a 50-50 chance of getting heads or tails. When you try to make some kind of assumption about what's going to come next, you're falling for streaks. You're falling for the gambler's fallacy. This is when someone watches a baseball player go up to bat 10 times and they miss it 10 times and think, oh, well, eventually they got to hit it, because they usually have bat better than 1 in 20 or 1 in 10. They bat better than that. That's the gambler's fallacy. Just because they missed the last 10 times doesn't mean they're more likely to hit this time. They still have the same chances they always do of hitting the ball, getting a home run or whatever. Your probabilities don't change because of past events. That's not how that works. So someone that sees the same result, they expect that the different result should happen. That's not the case. Previous results do not affect the probability. It's still 50% chance for either. So either one of these in the next flip is still a 50% chance. And when you try and start to make guesses about what it's going to be and say, oh, it's going to be more likely or less likely heads for the previous outcomes, you're falling for the gambler's fallacy. You're getting caught up in the streaks. So, it would be a different thing if I said, what are the chances of getting all heads or the chance of getting 3 heads? Those are different because those are lots of different outcomes where you get three heads. But when you look at this one pattern, again, this is just one outcome. That's just one outcome. And that's why they're not that different. They're both just one outcome. House edge. Okay, last thing to talk about. I mentioned this, I kind of explained this, but let's really just say it for good at the end here. Casinos make money because their games are set up so the expected earnings, the expected value for the gamblers are negative. And that's how casinos make money. They actually have the expected earnings or expected value for the gamblers are negative. So the EV, the expected value of the gamblers, is negative for the gamblers. So they know that on average, if a gambler comes and plays a game, on average they're going to lose money. Call it the expected value. For where the casino has the positive side, the gambler has the negative side, we call that the house edge. So the expected value, casino's earning, is called the house edge. And they set it up on purpose. It's legal and regulated. They're not cheating. This is just how casinos work. House edge does vary. It tends to increase for games with higher payouts. So if you have a bigger total jackpot, usually those things are going to have a higher house edge where the players paid in. Here I actually just did a Google search and looked up some values. So these were some of the things I found. So like blackjack is pretty low, right? Only 0.28%. But again, that means that if you keep playing blackjack, the casino is going to be taking 0.28% of your money on average. Yeah, blackjack's pretty even. This is actually pretty low. You'll see roulette's much bigger, 5.26%. So you play the roulette wheel now, they're going to take 5% of your money on average, so you're going to be losing more. Slot machines vary, but they can go anywhere from 2 to 15%. Again, this will probably depend on the price. Like the bigger, payout slot machines are going to be closer to 50%. So again, 50%, you might win and you might hit the jackpot, you might get that big payment, but on average, you're going to be paying 15% of your money into the casino. So for every dollar you wage, you're paying in 15 cents. Or if you for every $100 you wage, you're paying in $15. The casino, it lets you keep the other 85, but they're taking 15% off of all your, putting in there, and they're making money. They make more than you because you put in $100, you get 85 back. They get to keep 50% basically. And that's how the slot machine is set up. And again, you might actually lose all of your money. It might be someone else that makes that your 15% because they hit the jackpot. That's kind of what the casino does, is they take all the payout, pump it up to one thing, and then one person gets that big payout, but it really came from all those other people that already paid in. And in the casino, it takes in some more than they pay out, so they're, in the long run, making lots of money. Gamblers that think they can beat the house are falling to the gambler's fallacy. So if you start to try and come up with strategies like, oh, I've watched that machine for a while, someone's been losing a bunch of money, I'm going to go play it, I'm going to try and win, stuff like that, it doesn't really work because you're still paying in more than you get out. Typically, they're not as efficient as people like to think they are. They don't really work. Casinos have spent a lot of time and money over the years trying to figure out ways to ensure that people can't beat their systems and that they make more than they lose. They have tons of money already from the people they've taken money from before. They can put it to good use to make sure they make more money in the future. Now, I always feels a little bit like a downer because here I am harping at everybody to not pay in casinos and not go gamble stuff. And I'm not really saying that you shouldn't do that morally or anything. I'm just saying that if you go play a game at a casino, you should expect to lose money. You should expect to pay in. It's just like anything. You pay to go do something for fun. That's fine. And there is a chance you could win. Sometimes it happens. It's cool when it does. But people that get addicted to gambling and people that get stuck on this, they really don't understand the probabilities and the chances, and they get caught up and they think they're going to win, and it's not going to happen, and they just don't really understand probability. So on the very last page, I like to kind of end on a high note, maybe a little more interesting note for me, is after all this, talking about the house edge, the gambler's fallacy, all that kind of stuff, what are ways you could actually still expect to make a profit from the game of chance? And I've had lots of interesting ones over the years. I'll come up with a few of them. One is be the house. So if you own the casino, which I know most of us don't have enough money to buy a casino, but if you host the craps game, or if you run the raffle, and this is why schools and stuff like that, they'll do raffles, because they know that they're going to sell enough tickets that they're going to bring in more money than it costs to buy whatever item. So, be the house, run a raffle, run a card game, be the house at a card game, stuff like that. You could be the house, and then you have the house as you're working for you. You're going to make more than you lose. That's how those things work. Another is play for free. Now you're like, how can you play for free? Well, there are things you can do where you can like enter for free. So like when you walk by and there's a sign up stand, you can, hey, sign up and you can win this prize. Um, like I always think about like the surveys you get at Walmart. You get your big long receipt and you have the survey at the end. And you put it in, you get a chance of winning. Now, I will say, a little caveat, there's a lot of this side of things. They're just trying to get your information. So it's not really free if you have to deal with a bunch of junk mail. And so if that's something you want to avoid, well, then don't play those games. But you don't have to pay for the house. So the house's expected earnings are a little bit better. Again, these usually are set up so that there's very few winners for the number of applicants. So you're probably still not going to win. But you have better chances than, playing like the lottery or stuff, because at least this isn't negative against you. You didn't have to pay to play. So, like surveys, prize entries, that kind of stuff. You could maybe still win without, a bunch cost. Big thing is, understanding that typically games are set up against you. The companies, the casinos, the companies that are making these games, they have mathematicians, they have people come in and they run the numbers, and they know how to set it up so they're going to make more money, and you're probably not going to make money. So just watch out, be aware of that. I think this is something a lot of people don't understand. They just get caught up in things where they say, I might have a chance of this, but they don't realize their chance is so slim. They shouldn't even put their time or effort into that. Okay, that's it for this one. We got one more section for probably we'll cover on the next one. I'll see you then.